Okay, good morning. So let us start today's lesson. I want to keep this lesson a little bit short because I want to finalize the set theory. Then we will use the next section, the next session of this week in practice, and then you get 1 week for practice, and then, of course, this is week 38, yes? So week 39 you get time for practice, and week 40 you will have the exam, okay? I think it is good to finalize the lesson, whatever it is in the book, let us cover it today, which is a very, very simple lesson. And that is about the cardinality of the union of two sets. That's a very simple thing to understand. So if I give you two finite sets, my goal is to find a relation between the cardinality of this union. And can I discover a formula for the cardinality of the union? One probably immediate evaluation or judgment is that this might be the case. That if I want to count the number of the union of the elements in a set, I count the number of elements in A, I count the number of elements in B, and I add them. Okay, this seems reasonable, but I hope that you agree with me, this is not in general true, yes? Yes, because we are not allowed to repeat elements when we want to union things. So for example, if I have A is equal to AB, and then if I have B equals to, for example, B, C, and D, if I ask you what is A union B, then the answer is A and B, but B is repeated here, I do not repeat it, C and D. So if I ask you what is the cardinality of A union B, it would be 4. But if I ask you what is the cardinality of A, it is 2. What is the cardinality of B? It is 3. And if I add cardinality of A to cardinality of B, the answer is 5. And then you see that these two numbers are not equal. Yes? So in general, this is not the true equality, but I hope that you can also understand what is the correct formula for this. Yes?
Just add, subtract A, intersect it.
Yes. So the correct formula would be the cardinality of what is inside in both of them. Yes, so let me just write this as a theorem now formally. So yeah, let me clean this because that was simple. So let me write theorem. Let A and B be finite sets. Then the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of what is in the intersection. So if you want to understand it using Venn diagram, so if you want to have a proof for that, a little bit rigorous proof, let us consider that X belongs to the set of the universal set. Yes? So I just draw a diagram for better understanding, but my argument will not be based on this diagram, of course. I want to show that every element in the universal set is counted the same number of times on the left-hand side and on the right-hand side. So then it means that the cardinality of A union B is equal to this. So I just pick any element from the universal set that I like, and I want to show that this X is counted the same number of times on the left-hand side of this equality and on the right-hand side of that equality. Yes? So, for example, we can consider several cases. It might happen that X is not it is not in A nor in B, okay? So, how many times it will be counted on the left-hand side if this is the case? So, one possibility is that X is not in A and X is not in B. So what would be the contribution of x on the left-hand side? It doesn't count at all, yes, because it is neither in A nor in B. So the number of contributions of x for the left-hand side is 0 times. And then it is clear how many it will contribute here 0 times, because it is not in A. How many it contributes here 0 times, how many it contributes here 0 times. So 0 would be 0 plus 0 minus 0, yes? Let us consider another scenario. X belongs to A, but not to B. Because there are only 4 scenarios going on, yes? One scenario is that x is neither in A nor in B. One scenario is that x is in A, but not in B. If in this case, how many times we count x in this set, A union B? Once, it is counted once, yes? So I have one contribution on the left coming from such an x. Let us count the contribution of x on the right-hand side. Do you count x here? You count it once. Do you count it here? 0. Do you count it here? No, 0. So 1 plus 0 minus 0. Because if x is in A and not in B, automatically it is not in A intersection B, and you do not count it then, yes? So the contribution of this type of x's is 1 on the left and 1 on the right, yes? So if you face such an x, you are not adding anything to the left, you are not adding anything to the right. If you have an x, you are counting once on the left, you are counting once on the right, so they are matching. Of course, this situation is also similar. Yes, so let us just ignore that, that's the same idea. But another possibility is that x belongs to A and simultaneously x belongs to B. If you have this scenario, how many times do you count it in A union B? Once again. Because if it is in both of them, then you union them, you write them once, not 2 times, yes? So how many contribution comes from this type of x to the left? Once, 1, yes? How many contributions comes from such an x to the right formula? Do you count it here? So you have a contribution of 1 here, a contribution of 1 here. So 1 plus 1 is 2 times right now. But also you have a contribution here that you subtracted from here. So 1 plus 1 minus 1 is again 1. On the right hand side you have one contribution of such an x. On the left hand side again you have one contribution of such an x. So in this way you hopefully convince there are only 4 possibilities for these two sets. And in all cases, when I pick an x from the universal set, the number of contributions for any x would be the same for the formula on the left and formula on the right. So this is one way of thinking that these two are the same from a rigorous point of view, not from diagrammatic, not from the Venn diagram point of view. Yes? Is that clear? Okay, so let me just clean this, but it is very intuitively clear. So yeah, another way, of course, if I want to convince you, that's also good to know. Let me just draw another diagram. So here I have A, here I have B. So let me call this part A, this 1, this part 2, this part 3. Okay, so when I ask you about the cardinality of the union of this, I mean the number of elements in 1 plus the number of elements in 2 plus the number of elements in 3, agree? Because the union means everything inside this boundary. So in this boundary, I see there are 3 regions, distinct regions. If I want to calculate the number of elements in this boundary, it's clear that I count the number of elements here, here, and there, and I add them. But then, I can write this in this way. I can write it as the number of 1 plus the number of 2. And then instead of 3, I can write the number of 2 plus 3. But what I have done, I have added this. I have to compensate for that, I have to subtract. So what I have written, this is completely clear from this picture that the cardinality of A union B is this. What I have done, I have added this number. To compensate for that, I have subtracted that. So if you see what I have written on top is exactly equal to this. Yes? But if I ask you, what can you write instead of this? You can see that I am adding the number of elements in this region plus the number of elements in this region. So that is nothing except the cardinality of A. And the same thing here is cardinality of B. But if I ask you what is here, you see that this is the cardinality of what we call intersection. So that's exactly the formula. Yes? Understandable? It's very, very easy. So let me just write a remark here. Of course, this is very, very intuitively clear, but let me just write it down. Let A and B be finite sets. Then, okay, so what can you say about this? If you see the cardinality of the union is equal to the cardinality of this, this happens if and only if what? Under what circumstances this happens? Yes?
They are disjoint.
They are disjoint. Thank you very much for using that word. So this means that the intersection is empty. Yes? So only under this condition you can have this. And that's also very good to understand, by the way. So the cardinality of the union of two sets is equal to this if and only if the intersection is the empty set. So, for example, let me give you some examples. Okay, so let me read this question. So there are 35 students in a class. This is a very, very simple example. 15 students play football and 23 students play basketball. If 5 students play neither football or basketball, how many students do play both? Some type of these questions you might face using these ideas. Okay. The reason that I have written more on Venn diagram, even though I told you that here the Venn diagram is a way of intuitive picture here, but I would recommend you, instead of writing the formulas, I myself always prefer to solve these problems using the Venn diagram. Okay, but if you want also you can solve it rigorously. Okay, so if you want to solve it rigorously using this formula, so let us consider let us consider F to denote the set of the students who play football, and let us use capital B for the set of students in that class who play basketball. Okay, so what we know, I know by reading this text there are 35 students, but the last sentence is important because 5 students play neither football nor basketball. So it means that by reading this you understand that the cardinality of F union B, what is the meaning of F union B? And a student is in this set if that person is either in this set or in that set, or of course in both. Yes, that is the meaning of or in mathematics. So this means that when you write F union B, you are interested in those students who are playing at least one of these sports. That's the meaning. Okay, how many students do play both? So what is wanted from you? You want to find the cardinality of the intersection. This would be the number of students who are actually playing both of them. Because do you understand that this is the meaning of intersection? It means that the set of students who play football and play basketball. And that's exactly what we want to find. Of course, we also know that what is the number of students playing football? What is 15? And what is basketball? The cardinality here is 23. And then you want this. Okay, you have 2 question marks, but you need to know this. What is this number here? It is 30. Because 35 students, even though there are 35 students, but 5 of them doesn't play anything at all. So they are in the class, they are in this universal set, but they are outside F or B. Yes? So this, you need to know that this is what? This is 35 minus 5, which is 30. And then you write the formula F union B, and then you write, for example, this is this, minus cardinality of A intersection B. Instead of this, I put 30. Instead of this, I put 15. Instead of this, I put 23. And this is my question mark that I have to answer. So then it becomes clear that this is 30 is equal to 38 minus this. So then it becomes clear that the cardinality of F intersection B is 8. So there are 8 people who are actually in this class and playing both of them. Yes? Of course, that is completely okay, but I think for more complicated, because in the book you face some examples more that you are facing more than 2 sets and 3 sets. Okay, then you might think that, okay, it's better to have this Venn diagram. So both of them are acceptable actually in the exam. So by reading this text, you understand that this is your class, the universal set, and then you have a set containing the students which play football, and then you also have some students playing basketball. But because of the question, how many do play both, you might think that they might intersect. And the question is that you want to answer how many people are here. That is your question, yes? By reading the text, you understand that 5 elements are here. So 5 elements is in the box, but they are outside of those circles because they are playing none of them. But then, what can I write for this part? That is my recommendation. Always start with this one, you put it X, or if you have the number, put that number here, and try to write something here. So the number of people who are playing football is 15, and X of them is used here. So how many is left here? 15 minus X, and the same here, 23 minus X. So that's also one way of thinking about the problem. And then you can see that the total number of people in these 2 circles is given to be 30. So then you write 15 minus X plus 23 minus X is 30. And then you solve this one, again you find X is equal to 8. So that's up to you if you want to use formally the formal formula, or if you want to use a Venn diagram to understand it better and try to solve this problem. Yes? So that's up to you. Any questions? Okay. Now, there is another one, how we can extend this theorem to more than 2 sets. Okay, that would become a little bit more complicated. And of course, that's not part of your lesson if you want to go to higher and higher sets, but I can write the formula for you. You can immediately guess that. But let us at least, I think I saw it as an exercise in the book, let us find the formula for the case of 3 sets. We want to talk about the cardinality of the A union B union C. And I want to see that you immediately realize the formula becomes complicated. But there is a nice pattern going on. By looking at them, probably you could guess what would be the most general pattern, even though that is not part of your lesson. Okay, so, but before going that, let me also give you an exercise. What do you guess would be the cardinality of A subtraction with A minus B? So let us find a formula for that. So let me write an example before leaving 2 sets. Let A and B be finite sets. Then the cardinality of A minus B is equal to, using Venn diagram, it is actually more or less immediate. Can you just cook up a formula by imagining it in your head using a Venn diagram? This is actually why I told it's more on Venn diagrams. Just imagine, yes?
The cardinality of A minus the cardinality of A intersection.
Yes, exactly. Why you are hesitating? So here, at least from intuitive point of view, it's clear. You see here, I have A and I have B. I want to calculate the number of elements in this part because that is A minus B. Agree? It's very clear that if I count the number of elements in the total circle related to A, and then I know what this part is, if I subtract them, what I get is that one, yes? So your guess is actually completely right, and that is the formula. You can also use this the previous argument again for proving this formula, but let me present you another alternative here using algebra of sets. Okay, so one way is that consider an x and count the number of contributions of x for different situations on the left hand side and the right hand side, and show that in all cases these contributions match for both sides. Yes, this is one possibility. But if you don't mind, let me go to an alternative possibility that's also amazing to learn. I would say that let us do some algebra. How? First of all, I ask you do some algebra. Can you tell me, for any two sets A and B, if I intersect them, what will happen? If I union them, what will happen? Of course, you immediately can answer using diagram, but diagram is not actually mathematical proof. So can you just do it in your head intuitively, answer the first question mark, second question mark, based on the Venn diagram, which is good, but not a mathematical rigorous proof. And then we use the algebra of sets we learned and practiced last time, if you remember, to confirm that our guess is correct. So can you guess what is the answer to the first question mark? It's immediate. What is this? The empty set. Yes, it's the empty set. A minus B is this hatched part, and then this question mark is A intersection. If I want to intersect the hatched part with the part in the question mark, that's the empty set. Yes, is that right or not? Okay, so this is the empty set. Okay, now can you tell me what would be the union then? What? Yes, A. So these are our guesses, yes? And then of course we want to confirm that. Yes?
I don't understand the first.
A minus B is this area. And A intersection B is this area. And intersection is nothing. Yes? Okay, so how should I prove the first one? So let me call them number 1 and number 2. So I will start from the left-hand side. Okay, can you help me? We solve harder problems than this. Now I hope that you can help me. What should I write if I want to use algebra of sets to simplify this expression on the left-hand side? Yes? There's a famous theorem for subtraction. Yes? What is that? Yes, so I start writing that theorem for this, which we have already proven. Okay. So, what do you think here? Can I say that this is the right-hand side of a distributive law or not? Is it a distributive law? So do you remember what was distributive law? So I have A intersection B union C is A intersection B union A intersection C. So you see when or the other way around. If you see, the right-hand side of a distributive law is not like this, yes? Because here I am facing with intersections 3 times. But here I have 2 intersections, 1 union. They have to be different. So that is not the distributive law, but we know that they are commutative and they are associative. So it doesn't matter how I group them, how I reorder them. So what is in my benefit? In my benefit is that if I put them in one group and put them in one group, yes? So then it becomes A intersection B intersection B complement. But we know A intersection A is A, B intersection B complement is empty, and A intersection the empty set is the empty set. And that's the right-hand side. So our guess was actually mathematically confirmed. Number 2, so now I start from the left-hand side again, but A minus B is what? A intersection B complement. Now union A intersection B. Is this the right-hand side of a distributive law? In this case, yes. Because 2 of them are intersection, 1 of them is union, so I can talk about factoring out something, yes? So I can factor out A intersection from this set, B complement is left. from this union and from this B is left. But we have a formula for B complement union. B is the universal set. So I have A intersection, and this is the universal set, but we also know A intersection with the universal set is the set A itself, which is the right-hand side. Yes? So we actually confirmed that as well. Now I ask you one question that I want you to answer me. If I ask you, so here, let me try to tell this. If I give you a box, whatever a set is, intersection with whatever inside, if I guarantee that the intersection is empty, and if I ask you about the cardinality of the union of these two sets, what would be your answer? Actually, that's exactly the same thing that I wrote before cleaning this, yes? I am telling you, I have one set, I don't know what the form of that set is, what the form of this set is, but I confirm that the intersection is empty set. So what can you write about this? Just tell it.
0.
No, this is union. The cardinality of the intersection is 0. What the cardinality of the union is? Pardon? Why are you silent? What's the answer? If you look at your notes, I wrote a remark, but there I used A and B, yes? If the intersection of two sets is empty, you don't need to memorize. You had an understanding. After I taught you this, you actually are confused now. So, what?
Square plus O.
This one plus that one, yes? I don't know why you're confused sometimes. So I told you, so you were able to guess this before I teach you, yes? Is that understandable? If I have two things that are, okay, now I want to give the role of the box to A in minus B. I want to give the role of the circle to A intersection B. Yes? Yes or no? I know that the box intersection, the circle, is empty. Yes? So it means that A minus B intersection A intersection B is empty. So this means that the cardinality of this is equal to the cardinality of the first one plus the cardinality of the second one. I want to wait for you. Do you understand what I have written here is correct? Why it's correct? This is something I hope that you now know. You remember, the only problem that this is not equal to this is because sometimes this intersection is not empty. But if the intersection is empty, it is guaranteed that the cardinality of the union is the sum of the cardinalities. Yes or no? Okay? Now, I am telling you that, do you agree that the intersection between these two sets is the empty set? You should say yes, because we have the confirmation here. Now I am telling you that because this set, intersection with this set is the empty set, if I want to, I can conclude that the cardinality of the union is this one. Yes? That was my mistake. Yes or no? But now I ask you, what can I write instead of this now? You see the second line is A. So that is A. So that becomes the cardinality of A is equal to the cardinality of A minus B plus the cardinality of A intersection B. And I am interested in this as a question mark. So I move this to the left-hand side. It becomes cardinality of A minus the cardinality of the intersection is equal to the cardinality of A minus B. So this is another alternative way of proving this, which actually is important. Might be you do not appreciate it that much, but if you study probability, then you have some axioms. So if you want to prove other theorems in probability, the only things that you have in your hand to use them are algebra of sets. Okay? So this is the way that you can prove it. For example, this can interpret itself as the probability of A happens an event happens but B does not happen is equal to the probability of A happens minus the probability of both of them happen. Okay? So, but we don't study these things, so this is why you might say that, okay, this was very simple to understand. Why Bobak is making it so complicated? It's because if you want to understand probability from an abstract point of view, you have to do these things. So I would call it an optional exercise, but I want you to understand it was not hard to understand rigorously. But intuitively, if you want to use the formula, you are free to use it because it was very simple to imagine by just diagrams. Yes? Understandable or not? Okay. Now we want to go to the 3-case scenario. Okay? Here, I saw it as an exercise in the book, or I don't know, in the body of the book, so we have to learn how to prove it rigorously. And if I want to consider different cases, as I did before, consider an x, so let me write this as a theorem as well. So theorem, even though this is an example, but if you want to use it, you can use it freely. I don't think it is in the formula sheet, but anyway. Let A, B, and C be finite sets. Then the cardinality of A union B union C is equal to. Okay, so let us try to imagine this before writing the formula here. So if I want to imagine what is going on, so let me draw a Venn diagram. This time 3 sets are involved, so let me consider this most general case, that we have mutual intersection between them. So what I am interested in, I am interested in understanding the total number of elements in the union. If I want to represent the union for you, so let me just draw the border of the union. Yes? So whatever is inside this red boundary is the union of 3 sets. Yes? Is that understandable for everyone? Okay. Now I am interested to count the total number of elements there. Okay, so how should we do that? So let me start writing, yes? Yes, let me put letters inside, yes? For example, let me call the number of elements in this part x, for example. And let me consider this part y. And this part z, I don't know, t, u, v, I don't know, s. Yes. So by s, I mean the number, not the set. The number of elements in this region. By y, I mean the number of elements in this region. By x, I mean the elements in that region, etc., etc. So, it is clear if I ask you to answer this, the left-hand side here is equal to x plus y plus z plus t plus u plus v. By the way, w is a better one, yes? So, w, yes, let me write w. So, that is the question. It's clear from the Venn diagram there is nothing mysterious going on. I just need to add them. Okay, but can I write this formula in a little bit nicer way so that the cardinality of A, the cardinality of B, the cardinality of C, and some cardinality of intersections are also transparent in the way that I am writing it here? So for example, x plus y plus z plus w. What can I write for this? Cardinality of A, yes? So I can write cardinality of A, yes? But what is left for me is 2t plus u plus v. Yes? Okay, what can I do? can I write cardinality of B here? T plus U plus V. No. Yes? So if I want to make it the cardinality of B, what should I do? If I want to have the cardinality of B here as well. So B and T, X and Y. So which one I have? I have V and T, so that is good. So let me write it as cardinality of A. I'm trying to discover that, okay? So then I have T plus V. What do I need that I do not have? I have X and Y, so let me add them and don't forget to subtract them. Yes? And then of course I have, do I have T? No, T is used, V is used. Okay, one U is left. Let us double check. Do you agree with me now? What I have written is correct. But what can I write instead of this one? Cardinality of B. Okay, but then if you agree with me, here I can factor a minus sign, it becomes X plus Y. But what can I write for X plus Y? Yes? B. Yes, is that right? So instead of this one, so I write minus cardinality of what? A intersection B, but unfortunately still I have a U left. Yes? So far it's very good. Everything is written in terms of the capital A and capital B, but unfortunately U is left. So what can I do with U? You can discover it. You see, it's very simple. So A plus B minus, what is this one? So let me just repeat this. I want to have it, but I do not want to have U. But unfortunately U is here, so I have to write what? Can you tell me? I have to write U plus X plus Z plus T, and then I have to subtract them. Yes? So minus X plus Z plus T. Agree? Okay, so now if I continue, I have this, and that, so it becomes cardinality of A, cardinality of B. But what is this one? It's cardinality of C with plus sign. And then I have minus cardinality of this. And then, unfortunately, I have this one, but I can organize it in this way. I can write minus X plus Z minus T. Do you agree? I just multiply this minus sign for these two and multiply this minus sign for T. But now, if I ask you what is X plus Z, you can answer. It is the cardinality of the intersection of A with C. Yes? So this is cardinality of A with C. But then, unfortunately, T is left now. So how do I get rid of T? Yes?
You could write the coordinate of B intersect C and then subtract that by the coordinate of A intersect B intersect C.
Very good, yes, that's good. So then all of them comes into the game, yes. And then that is the last thing that we want to do, yes? So it becomes equal to, so let me just write this. So copy and paste cardinality of A, cardinality of B, cardinality of C, minus cardinality of A intersection B, minus cardinality of A intersection C. But as you said, what should I write here? Instead of T, instead of minus T, I write minus T plus X, but plus X. I hope that you agree with me. If I multiply minus sign inside, it becomes minus T minus X. Minus X and X are cancelled. So what is left is minus T. And what I had is exactly minus T. So instead of minus T, I am allowed, if I wanted, to write such an expression. Understandable for everyone? But now if I ask you, can you write this better? You would see that T plus X is the cardinality of the intersection between B and C. So this becomes the cardinality of B and C. And if I ask you what that X is exactly in the middle of the three of them. So it is the intersection of all of them. Yes? So it becomes the plus the cardinality of A intersection B intersection C. So if I want to write this formula here for you, this is the cardinality of the first one plus the cardinality of the second one plus the cardinality of the third one. And the sign changes. minus the cardinality of every intersection of every pairs that you can imagine, A and B, B and C, or I don't know, minus C and A. The order is not important. And then you need to remember, you have to add the cardinality of the intersection of all of them. So you see that the formula becomes a little bit more complicated. But hopefully, by having the case for the 2 sets and having the case for the 3 sets, you might be able to guess for higher number of sets. By the way, for higher number of sets, you have to work rigorously. It's also a nice exercise. If I want to draw 4 circles, here I have drawn 3 circles. Mutually they intersect. This one with this one intersects, this one with this one intersects, this one with that one intersects. If I want to do it for 4 and I want to have it every pair intersect, that might be hard to draw, but for the 5 number of sets and 6 number sets, probably that is not working at all. So this is why we need a mathematical argument for that. But hopefully you can read the pattern. First of all, let me ask you, anyone has any questions how we got this? But this has limitations. This is why we have to go to another way of doing things. Yes? This has a limitation that this is correct for this picture that you have here. You might say, how do you know that this is also true for this case? You need to convince yourself that if the sets A and B and C are in this form, this is also true. So then there are a lot of things that you need to consider. So it is not a rigorous proof, but it is a very intuitive way of finding something. It's exactly according to your intuition. But let me just do it as an exercise rigorously, but I think you should be able to do it. If I want to do that, what is your suggestion? So I want to find a formula for A union B union C. What do I have right now is the formula for the union of 2 sets, but I want to say something about the union of 3 sets, the cardinality of the union of 3 sets. So let me just repeat this here. Can you tell me what is the cardinality of a box, union, a circle, whatever inside them? It is the cardinality of the first one plus the cardinality of the second one minus the cardinality of the intersection. So we just proved this. The proof of this was rigorous because there are not many cases involved. How can I use this to find the formula for that? This is considering 2 sets. My problem is considering 3 sets now. But there is a standard method for that. Yes? Yovian, do you want to say something? No, intersection is a little bit later. But right now, the starting point. How I should look at 3 sets? The sum of 3 numbers is actually the sum of 2 numbers. You can view it as the sum of 2 numbers, yes? The second number is the sum of the second term and the third. The first one is the first one. If I write 2 plus 3, you know it's 5. When I write 2 plus 3 plus 6, you also know the answer. But you can view this as the sum of these 2 plus that one. And that means the meaning of associativity. It doesn't matter how you collect them. And that is the same here. So if I want to answer this, I can myself interpret it as 2 sets, as the union of 2 sets. I can interpret it as A union B union C. Now I can give the role of the box to this, and I can give the role of the circle to whole packet there. If I ask you now how many sets are involved in your problem, you would say 2 sets. One of them is called A, the other one is called B union C. Is that right? So now that I have the formula for the cardinality of the union of 2 sets, then I can write and use it. So can you help me to write what I want to do? What should I write first? Cardinality of which set? A plus cardinality of B union C minus cardinality of an intersection between them. So it becomes A intersection B union C. Agree? So far so good. If someone asks you what you have used, I said that I used the formula for the 2 set case, and I was able to show it rigorously. But then I hope that you understand at least you can do something for this term. Because that's also the cardinality of the union, but how many sets again? 2. So I know what to do with that part at least. So what I do, I would write the cardinality of A. Instead of the second term, I write the cardinality of B plus cardinality of C minus the cardinality of the intersection between them. But the hard part is what to do with this one. Do you have any clue? Yeah, I heard a little bit, okay, I think the correct word. What should I do here? Yeah, distribution, yes? Because this is A intersection B union, so what can I write? I can write A intersection B union A intersection C. Yes or no? That is the distribution. But now what happens? How many sets again are involved in this union? 2 sets, and I am interested in the cardinality. So the cardinality of the union of 2 sets is again the same formula. So I can use it again. So what happens if I want to continue? I have a minus sign here. So let me put a big pair of brackets here. And can you help me to write something in the pair of brackets now? What should I do? Do you understand what's going on? Or no? Thank you. Yes, A intersection B, A intersection C, intersection. Yes? Is that understandable? So you see that I am answering this question for the case of 3 sets only using the formula for 2 sets, which I have already rigorously shown it to be true. And one more thing, I use one property here, associativity, and one more property here, distributivity. Yes? So now you might say that it seems like a circular argument, but it is not, because this is the end of the story. What can I write instead of this? A intersection B intersection A intersection C. Is this distributive or commutativity or associativity? Is it distributivity? No, because all of them are intersection. So it means that if I want, I can recollect them and reorder them. It would be my benefit if I put these 2 next to each other and these 2 next to each other. Yes? Why is that? Because I have an answer for this, which is A. Do I need these pair of brackets? No, because all of them are intersection and it's associative. Yes? So this now everything is finished. So it becomes cardinality of A plus the cardinality of B plus the cardinality of C minus cardinality of B intersection C minus cardinality of A intersection B, again minus cardinality of A intersection C, but minus times minus is plus cardinality of A intersection B intersection C. And that is the rigorous way of proving this. So the way that I showed it here is independent of my drawing abilities. Even if I have 10 sets involved, and it is hard to imagine how to draw them, but this method is actually working. Of course, it becomes a little bit more complicated if I increase the number of sets. But in principle, you know what to do. If I have 4 sets, what can I do? If I have 4 sets, I can view it as 3 sets, or I can view it as 2 sets. It depends on my collection. For example, if I have A union B union C, union D, if I want, I can write A union B, I don't know, together with C union D. But how many sets are involved again? 2. And then you can do a lot of algebra to come to the answer. But the pattern will continue. Can you guess what would be the pattern for the next case? So let me clean the board. But that is the end of your lesson. This is the final formula in the book. You do not have any formula for higher number of sets. But I am just trying to see that if you can guess the pattern. might be it's not that clear yet, but let me see how much you can be creative in guessing these things. Educated guesses are actually very important in mathematics, by the way. So can you just write a formula for this one? This is just as an optional exercise. You don't need to be worried about that. But what do you think would be the answer to this? Yes?
Cardinality of A plus cardinality.
This is clear, yes? Cardinality of A, at least the first few sentences is clear. Cardinality of A plus cardinality of B plus cardinality of C plus cardinality of D. And then?
Minus A, cardinality of A intersection B.
Yes, so let me minus A with B.
Minus A intersection C. Minus A intersection D. Minus B intersection C.
Yes, very good.
Minus B intersection D. Minus C intersection D.
Yes. Okay, the next plus, yes.
A intersection B intersection C intersection D.
Yes. No. You are too fast. So the thing is that after the having pairs, you need to go to triples. And write all the triples and then go to the one containing 4 of them. So the formula is really complicated. So then it becomes the cardinality of A union B intersection C, A intersection B intersection D, and then I have the cardinality of A intersection C intersection D, and then I have cardinality B intersection C intersection D, and then every triple is finished. Now I go to the intersection of all of them, which sign? No, this time minus, because they're alternatingly changing. So it becomes minus A union B intersection C intersection D. Yes? So that would be the formula for the case of 4. And then you can probably guess what will happen if I have 5 sets. So the formula becomes very complicated. But the pattern is not that complicated. Yes? But keeping track of all pairs, keeping track of all triples might be a little bit hard. But you understand. You have to consider all single sets, all possible pairs, all possible triples, and all possible quadruples. Yes? And then, of course, I don't know what is the next one. What is the after quadruple? Yeah, I don't know. The next, you need to consider all of those cases as well. Okay. So this is the way, but you don't worry, if you are worried about, you need to just end up here. Any questions regarding this? Okay, so if you don't mind, I will give you one single example that you can use in practice this kind of problems, and then the lesson will finish. And the set theory actually is finished, but on the next session, I will try to bring some collection of exercises for you to solve, and then the next week, I will not teach at all. Both sessions you just practice, and on week 40 we will have the test, okay? And some of you, I see that you haven't submitted actually the quizzes. It doesn't matter for me because I have written that is just for your own evaluation of how you progress in the course, but I really recommend you to do them, okay? That's up to you. Okay. So what I mean is that if you don't even do one single quiz and you get A, your grade is A, regardless of if you haven't handed them in or not. That's what I'm saying. But I'm trying to motivate you to do them to actually pave the way towards a better grade. Okay, so let me pause the video because there are some problems that, of course, you can write the formula and use the formula. But the harder problems is that you have to have some interpretations about them. So this is why I start with an example which you don't want to exactly do this. Or okay, let me write this one first. Okay, let me read this question if there is nothing wrong with it. I hope that these numbers are correct, because otherwise if I have made them wrong, you might end up with a negative value, which is actually nonsense. So in a school with 380 students, 215 are taking biology, 173 are taking physics, 182 are taking chemistry, 72 are taking both biology and physics, 90 are taking biology and chemistry, 60 are taking physics and chemistry. If 9 students don't have any of these courses, so I don't know what they are doing in the school, but anyway, how many students are taking exactly one subject? Yes? How many students are taking exactly one subject? Because this problem is not hard in nature, I would recommend you, I pause the recording, you think about it, and I think I have the solution here if I haven't done it wrong. If that's correct, we can continue solving the problem. So that would be the final example for this lesson today. Okay, if you don't mind, let us solve this problem so that we can finish everything before the lesson ends. So I will use the method of Venn diagrams here, if you don't mind too. So here in a school with 380 students, so let me just draw this universal set here is the school. So let me just keep it universal here, and then we have 3 subjects. Is biology, physics, and chemistry. So let us keep B for biology, physics, and chemistry. Okay, so 9 students does not study anything, so 9 students are here. 9 people are there, so, and then we have 215. Okay, what I do, is there any, okay, so we don't know this part, so I will start putting X here. I don't know how many students are there. Okay, but then let us not increase. I can give different letters to everything, but that is not very good. Try to keep the number of unknowns as minimum as possible. Okay, so try to read the information and write whatever you need there. So here, for example, I go here. So 72 are taking both biology and physics. So biology and physics is how many? Please help me. What is how many? 72, yes? Biology and physics is 72. X of them is here, so what is left for here is 72 minus 6. Yes? Don't keep different letters. Of course, in principle you can, but it becomes very messy. I go and read how many people are there between biology and chemistry. How many of them are studying both biology and chemistry? How many of them? 90. So X is here, so this contribution would be 90 minus X. And then physics and chemistry, 6, how many? 60. Okay, 60. So it becomes 60 minus X. Please check my calculations. Okay, so far so good. And then what I want to do, I know that, so by the way, which is the question mark? The question mark is which part? I want to see how many students are taking exactly one subject. Yes? Exactly one subject means the number of elements here, this interpretation is on you. If I ask you what is in common between these people in this border, you would say that they are studying only biology, nothing else. But they have asked you about how many are studying exactly one subject, so it means that you also consider this one. Yes? You should also consider this one. Yes? So for example, if I call this subset X, this subset Y, this subset Z, I am calling these regions X, Y, and Z. So the question mark is the cardinality of X plus the cardinality of Y plus the cardinality of Z. Yes? This is what I want to know. but I also have something extra information. I know that how many students are involved at least in one subject, 371. So 380 minus 9 is 371 students are actually taking courses. Okay, but I also can write something for the cardinal, because what is cardinality of x? Cardinality of x is the number of students studying biology, which is how much? 215 minus 72 minus x minus 90 minus x. Yes, and I have to calculate this. So this is 162. How much is that? 53, yes? Plus x minus x are gone, plus x. Am I right?
Yes.
So that is this. What is the cardinality of y? The cardinality of y is the number of people studying physics, which is 173 minus 72 minus x minus 60 minus x. So if I calculate this, it becomes 101, 51, no, 41.
41, yes.
And then x and x are gone, and again plus x. And then finally, if I ask you what is the cardinality of z, I'm not saying that this is probably the best way to do it, this is probably one way. And then if I go to the chemistry, how many people are studying chemistry? 182 minus 60 minus x minus x minus 90 minus x. So then what happens? 122, 32, please correct me if I'm wrong, and then plus x. So the question mark that I am looking for is the sum of these three. So x plus x plus x is 3x. And then if I add them, it becomes 70, 123, 125. Yes? So 26. This is my question mark. So the only problem is that I can find x. If I can find this x, then I can answer this question. Okay, what is your strategy to find x? You know that if you add all these numbers, should be 371, and there is only one x involved, and you can find them. So if I add them, 3x plus 126 is this part plus this part plus this part, plus these four parts, plus 72 minus x plus 90 minus x plus 60 minus x. This should be equal to 371. Yes? All these parts together should be 371. And you see that in this equation there is only one unknown, and that is x. If I start adding them, minus x minus x minus x minus 3x, this is gone, so x is left. And then I have to add these numbers. So what is that? 198, and this one 288, 348 is 371. So x is 23. Yes? Probably I'm not saying this is the best way. I might confuse you, but you can find probably. But this is the way that you can do it. This is a trivial problem. And then you have to put this x back here because your question mark is this. And you multiply it by 3, it becomes how much? 69. 69, 125. 26 is exactly 195. So this means that x is 3 times 223 plus 126, 195. So that is the answer which is demanded in this problem. Might be, I don't know, might be if you think a little bit better, you can find a better way. Might be I'm convoluting you a little bit, but this is one way to do that. Any questions? So yeah, what I'm saying is that the problem is trivial, but it might need some calculations. I will bring some more problems here, more interesting problems probably next time. So next time we will practice together, but the next week you practice on your own. Any questions? Okay, thank you.